Alright, so this is a continuation of my video on taking a look at our AEM 648 theory of plasticity final exam, which is to use the Prager-Ziegler Harganing rule. So, as kind of review from what we talked about last time, we have a load path that initially starts out parabolic. I found out where the load path goes and crosses or reaches the yield surface. And beyond this, we're going to have some plastic flow. We have some additional load segments, and if I plot out what the total path looks like in phase space of tau x, y, and sigma x, it goes parabolically here, straight down, and then straight over. We're going to use Prager-Ziegler kinematic hardening, and for that, I sent a handout to the class, and we're going to use some of these equations. I've decided to write this in regular stress space, so with the non-spherical hyperellipsoid. But we're going to use our von Mises yield criterion, or J2, easiest written in deviatoric stress space, but we're going to use this version here. Prager-Ziegler says that d alpha, the movement of the back stress, is equal to some constant times the difference between the current stress state on the surface and the current back stress state. So d alpha will move along a line that's parallel to this direction. So it's not necessarily in the direction of the applied stress increment, which could be loading off at any particular angle, but it is parallel to this path. Now d mu is determined by the consistency condition, which says that the yield surface must, the current stress point must stay on the yield surface during plastic flow. And if we go through the consistency condition, we can show that partial of f with respect to sigma is equal to minus partial of f with respect to alpha. We're going to use that information in order to come up with d mu, which is going to be partial of f with respect to sigma dot d sigma, partial of f with respect to sigma dot sigma minus alpha, or in index notation we can write it as such. Now when we have already moved off of the original origin of the stress space with our yield surface, we'll want to cast this in terms of xi, so partial derivatives of f with respect to xi. We want to make sure that we have the right, the correct travel from, we want to have the right normal to that yield surface. So we're going to write it in terms of this, partial f with respect to xi, so that we're offset if we happen to be off of the center of the stress space. Alright, so here's kind of a flow chart about what we're going to do. It's not necessary to go over this in any particular detail, but we are going to use a constant plastic tangent modulus. So the effect on our stress strain curve will be bilinear in the total stress and strain, so we go up and then over. And we're going to use our normality flow rules that says that d epsilon ij plastic is equal to d lambda n dot d sigma in ij. We're going to do this in terms of the regular stress space. So with our partial derivatives, we'll be able to find our unit normal, and then we'll know our d sigma. So let's take a look at the spreadsheet that I've got set up so far. There's going to be a couple improvements that I'm going to make before I get to my final calculation, but I want to kind of show you at this point how I've got it set up. So that'll go into here. I guess maybe we take a look at our partial derivatives real quick. Here's our yield function. Sigma naught squared. I squared both sides. The von Mises criterion. I rewrote it, expanded terms out as this function, and then I took partial derivatives with respect to each of these components. Now notice the one thing that I've done here is I have decomposed the shearing stresses into a tau xy and a tau yx. For me, it's always easiest to work with the 9-dimensional stress space than it is the 6, and that avoids me having any errors when I take some partial derivatives and evaluate things. So that's what I've done here. So I have these 9 partial derivatives. Alright, now let's take a look at our first loading step. Here is my stress state. Here's the stress state that I found to be on the yield surface. Here's my initial alpha vector, and here's my initial xi vector, which should be the same as sigma x, and it is. And I've just copied that down here. So what I'm going to do is I'm going to look at this stress state, which is a little increment away from the initial stress state. I still have my same alpha and my same xi, but really what I need is from this step to this step, I need the d sigma. And that's going to hold a key to a lot of things that we're going to be looking at. So the d sigmas are nothing more than the previous minus the current minus the previous stress component. And so again, I have these 9 terms here. I did go ahead and calculate the hydrostatic stress. In this case, I'm not using the deviatoric stress space, so we're just doing it in that fashion here. Here are my partial derivatives. Okay, so 2 times this value minus the other 2. So we're doing this on xi. Here's the magnitude. So here's the magnitude of this vector, and then I turn it into a unit vector here. Now, we do need to make sure that we are actually loading and not unloading. And so here's the n dot d sigma, which is positive, which does indicate a loading increment. If this was 0, that would be neutral loading. If this was less than 0, that would be elastic unloading, and we need to not do any plasticity calculations. We just need to use Hooke's law and find out where the yield surface and the stress vector intersect. Alright, so if we go back to our page, the d mu calculation is partial f with respect to sigma or psi dot d sigma, partial f with respect to xi dot sigma minus alpha. So this is the top of it, and this is the bottom, and that's what these terms are here. Partial of f with respect to sigma dot d sigma, partial f with respect to sigma dot sigma minus alpha. And so that d mu is the ratio of those two. From that, I can calculate my d alpha. Again, if we go back to our page here, the d alpha is d mu times xi. For the plasticity calculation, I need the d lambda, 3/2 1 over h. And then we have our plastic strain increments. N dot d sigma times d lambda times the n vector. So that's what each one of those are. And this is based on Hooke's law now for the elastic strain increment. And if I want the total strain increment, and I've made a note here that these are tensor strains at this point, I take the elastic and plastic increments and I add them to my previous value of my strain, which was based on Hooke's law, which is here. Okay. So with that, now I have associated with this state of stress over here, state of strain that goes right here. Now, I'll do this in a separate video. There's a couple things I need to do. I need to update my alpha vector based on the values that I have for d alpha. So it would be the previous alpha plus the d alpha. And then that will update my xi, and then I'll just keep going through this process until I move along. Now, one thing that I noticed as I was looking at the spreadsheet, my first increment is pretty small, and even my second increment is pretty small. I'm probably going to have to go back and refine these increments of the stress so that I have smaller changes in stress. My rule of thumb is I kind of like to be around 1 megapascal or so. So what I'm going to do is I will add more terms to this load path. You see how it's kind of refined near the yield surface intersection point. But I'm going to go ahead and put a few more points in here so that I can get smaller stress increments. Alright, we'll see what happens. We'll pick that up at the start of the next short video.